So yeah, so typically ADCs or general lot of analog circuits are characterized in frequency domain. So that's why it's important that you know this. So what I'll do is we'll take a short detour now, brush up something on spectral analysis, and then we'll come back to this. Okay. And as you see, with respect to ADCs, we are dealing with both a sinusoid, which is a deterministic signal, and you have quantization noise, which is a random signal. So we'll do for both these guys. So let's start with deterministic signals. And you guys know what is a deterministic signal. Its value at any time instant is known a priori, right? And let's say have some x of t, continuous time thing. To find the frequency spectrum, you resort to continuous time Fourier transform. So you find, let's say, x of f as integral j2 pi ft dt. Done? Everyone knows. So let's say my x of t is a voltage signal, so it has units of volts. What is the units of the Fourier transform? What is the unit of this fellow? It's unitless. What is the unit of this guy? So this is basically, I'll say, volts per hertz. So you can treat this as a voltage or amplitude spectral density. Again, this is same thing as your probability density function. It's a density function. So all that means is, if I find that my if the Fourier transform of my signal at some frequency f naught is a naught, it doesn't mean that the signal has a sinusoid at a frequency f naught with a strength a naught. Okay, it's a density function. So all this implies is around this guy, around this frequency in a 1 hertz of bandwidth, I have a whole continuum of sinusoidal frequencies, and the combined strength of all of them is a naught. It's like a probability density function. Just because my PDF is non-zero at a particular point doesn't mean the probability at that point is that. In fact, single point probability is 0, right? So here also, unless you have an impulse, you cannot say that my signal has sinusoid. If I have impulse, yeah, then I know for a fact I have a sinusoid at a frequency f1 with a strength a1. Area of this impulse, yeah, strength is the amplitude for the sinusoid. Because these are all density function, it just says in a 1 hertz bandwidth, as you see from the units. What is the deal? It doesn't give a single point information. In fact, technically, I can say that the strength of a sinusoid at a frequency f naught here is 0. Because a naught is the strength of all infinite sinusoids. For a single sinusoid, it's, I'll say, a naught by infinity, loosely speaking. Right? So this is something you should understand. Yeah, of course, this is now in continuous time. We also have discrete time Fourier transform. We saw probably in the last class we touched upon this. So it's just the same thing, n equal to 0 to infinity, x of n e power minus j omega n. Same thing. The only difference is in continuous time, the frequency goes from 0 to infinity or minus infinity to infinity. Here in discrete time, omega is basically periodic with 2 pi. Right? So you look at any interval, let's say minus pi to pi or 0 to 2 pi. So hopefully this is fine. So yeah, so now let's look at random signals. So as you know, random signal is something which you can't predict. Its amplitude is not known. So once again, you deal with statistics. So like mean and mean square. So most of the random signals we deal with will have 0 mean. So the only statistical quantity that is of relevance or significance will be the mean square value or the power of the random signal. Now of course you have a spectrum for random signals also. Now for deterministic signals, the main information was in the amplitude. So it made sense to define an amplitude or a voltage spectral density. For random signals, I see the only relevant piece of information is in the power. So instead of for voltage spectral density, you kind of define a power spectral density. I'm just giving a very hand-wavy explanation for all of this. That much is enough for this. Okay. And what do you guess the units of this will be? Yeah, it's volt square per hertz. Again, it's a density function. It gives the power around a particular frequency in a 1 hertz bandwidth. Okay. Right. So so I know that if I take Fourier transform, I get something with volt per hertz. I want something which is having this units of volt square per hertz. Can you guess what can I do? If I take x of f that has volts per hertz, I want something which has volt square per hertz. What can you do? Simply to if I take square, what do you get? I need something to, if I divide with time, that's all, right? That's all. And typically, how long do you think this time should be ideally?
For interval.
What is interval? It's a random signal, it's not repeating, right?
All time.
It's like any statistical measure, you do this for infinitely long time, in theory, only then you will get the right thing, right? So this is how it is done. So limit t tends to infinity. One minor variation, one minor changes, you actually take an averaged Fourier transform. That is, you find magnitude squared Fourier transform, repeat it multiple times, take an average of it. This is how power spectral density is defined. Okay, there is nothing you can do. So I'll say Sxx of f. We'll see why averaging is important in a minute, but this is the definition. And yeah, one thing to remember is this PSD is an even function of frequency. So whatever you have in the negative side, you will have the same thing happening in the positive side. So this is called as two-sided PSD. Since you know this guy is symmetric, you are not gaining any information by plotting both sides. So sometimes you just show only one side. You take the negative side, add it onto the positive thing, and just plot a one-sided PSD. Okay. And the intuitive way to understand PSD is this. Let's say you take a signal x of t, you pass it through an ideal bandpass filter with a center frequency f0 and a bandwidth of 1 hertz. And if I measure the power at the output of this signal, or measure the power at the output of this filter, that will give me the power spectral density at f0. Again, it's power around a particular frequency in a 1 hertz bandwidth. In fact, this is how all practical, like measuring equipments measure this. But anyways, yeah. Which one? Yeah, you take any signal, pass it through an ideal bandpass filter with a center frequency f0 and 1 hertz band. Cool. So now you know that power spectral density gives power around a particular frequency in a 1 hertz bandwidth. If I want to find the total power in the signal, what do I do? Yeah, you are interested in the power across all frequencies. So you sum it across all frequencies in continuous time. This is essentially integration. One thing is, when I am integrating from 0 to infinity, I have inherently assumed that this is a one-sided power spectral density. Okay. So this much is enough for power spectral density, I think. So similarly, you can have the same thing in discrete time. So that is just repetition. Here again, instead of time, it's 1 by n, where again n tends to infinity in theory. Expected value of discrete time Fourier transform square. So, okay. The same thing I'm just rewriting, no big thing. again with discrete time, please remember that the discrete time frequency is periodic in 2 pi. So if I am drawing a two-sided PSD, for continuous time it can go from minus infinity to plus infinity. Whereas for discrete time, you have it only from minus pi to pi, it will keep repeating after it. Okay. So this might be for, let us say, discrete time, two-sided. One-sided will be something like this, from 0 to pi. Okay. Cool. So yeah, similarly, if I were to find the total power from my discrete time path spectral density, I'll have to integrate the PSD as usual. So if I take one-sided PSD, what will be the range of frequencies I'll do for integration? 0 to pi. Single-sided PSD, so this is same thing, Sxx of e power j omega d omega. One thing to always remember is whenever you have this operations done in omega, you will have a scaling factor of 2 pi. Omega means you'll have 2 pi. Here also, if I am doing it in continuous time omega, you'll have 2 pi. Remember this.
The units of discrete time frequency is not exactly.
There is no units technically, right? It's just radians. Yeah.
Why are we talking between minus pi only?
Because that is, I mean, if you remember, we saw in the first class sampling, right? Once you sample, the spectrum repeats periodically, and then even the discrete time spectrum keeps repeating. Cool. So the bottom line, for discrete time signals, you take the discrete time Fourier transform, magnitude squared, and then do this multiple times and average it, scale it by the number of points for which you have observed the signal. That gives an estimate of the PSD, right? And I will show why you need to do averaging. So what I have done here is I have generated a random sequence in MATLAB, which is supposed to have a flat path spectral density. Okay. I didn't do any averaging and directly did this magnitude squared, and the thing I get is yellow. As you see, there is a lot of variance over the expected value. Once I average it by, I think, 4 times, I get the blue one. Once I average it 10 times, it's fairly constant. So, oh, the same thing, right? Here what I'm saying is, when I'm doing this, the first case, expectation is basically taking average, right? So I took a sample of 0 to n point sequence, take magnitude squared of this guy, and then divide it by n. That was the first thing. Second time what I did, instead of taking 0 to n, I took 2n sequence long, split as 2 segments, computed magnitude squared Fourier transform for this fellow, averaged it, divided by n. And then if I keep doing it for more and more segments, I get a smoother curve. So that's what you typically do in practice. So let us say, for example, you capture 10n points, you split it into segments of n to n, so on, like this. Sorry. And then you take the magnitude squared Fourier transform for each of these segments and take the average of these 10 magnitude squared Fourier transform and then divide it by n. That gives an estimate of the path spectral density. So usually to increase this number of segments for averaging, what we do in practice is this. What you can do in practice is this, or I will say, see here, the first segment was this, second segment was this, right? So instead of having it like this, you can also have an overlap between segments. That is, I can choose this as my first segment, second can be this, third can be this, and so on. This way you will have more and more segments for averaging for a given data set. So it is expected that the variations in the measured or estimated PSD will also be smaller. And this is called Welch method of Welch estimate of PSD. And this is what you will also be asked to use in this course in assignments and stuff. We'll come to it later. What are they?
The second one is the Welch.
Correct. That is, I don't know, you can call, I don't know what is the jargon for this.
Sir, the greater the overlap, the better it will be as a respect.
Okay, but how long, what is the maximum you think you can overlap? What is the maximum you think you can overlap?
N minus 1, like 0 to
No, 0, I have n samples.
So you overlap at
One sample is fine, but you can do more, right? What is the maximum logically do you think you can overlap?
you start at 1.
From here.
Yeah.
I mean, you are saying this will be my first sequence, this will be my second sequence.
Yes.
That looks like I'm not gaining any new information, right? This is just one sample difference. See, averaging means there should be two different sequences that are getting averaged. If you average the same thing twice, you're not gaining anything. Right? So logically, what is the maximum overlap do you think I can have?
Half will be better.
Yeah, that's typically the case. You don't go more than half.
So each signal is the same over all segments.
No, you're trying to measure the path spectral density of a random signal, right? So you capture it for, let us say, 10 endpoints. Although you're taking endpoints sequence and finding its Fourier transform, you capture it for much longer duration and then do this. That's what it is. Cool. So again, this is the deal. So let's get back to our quest. Our quest was to find and characterize the performance of the ADC. We saw that in time domain it was not doable, so that's why we had to go to frequency domain. And here we saw, frequency domain, and that's why we did all this. So let's get back to this thing. So I am trying to measure the E knob, so I'm taking the ADC, feeding it a sinusoid with the maximum amplitude possible, and then I get some quantized discrete time sequence at the output, and then I'll have to take the, let us say this is Y and this is V. I'll take SPV of e power j omega, the path spectral density. It's discrete time sequence, so I'll have, if I plot the single sided PSD, it will be from 0 to pi. Now my signal has two components. One is the input signal, second is the quantization noise or the quantization error that I have added in quantizing. So my spectrum will contain both these fellows. How do you think the spectrum of the sinusoid will look like here? A sinusoid, if I look at its spectrum, it's an impulse. The sinusoid is just an impulse. Fine. So I expect to see an impulse here. Now I'll also have the quantization noise. So we need to find out what will be the spectrum of the quantization noise. Now, I mean, you tell me for the quantization noise, to find its probability density function, did we do any analysis or what did we do? For making statement about PDF of the quantization noise, what did we do? We just made an assumption. So here also we need information about its PSD. What do you think we can do? Assume. And what is the simplest shape you think you can assume for the spectrum? I mean, okay, flat, that's what you mean, right? Yeah, so that is a different name. So that's what we'll do. So already we made two assumptions. One is it is random. Second, it has uniform PDF. So the deal is it won't hurt to make a third assumption. And the assumption is it has a flat path spectral density from 0 to pi. And this is called as a white power spectral density. Again, call back to white light, which has all frequencies, right? That's all. So that is what is assumed. So again, remember that the quantization noise power, what was it in terms of step size delta? It was delta square by 12. We saw that. So from here also you can find the noise power by doing this 1 by 2 pi integral 0 to pi SQ of e power j omega. This will be equal to delta square by 12. From this you can find what the site is. Right? Cool. So now if I plot the spectrum at the output, let me copy this. So my sinusoid will have this impulse, my quantization noise will have a flat spectrum, right? Now from this I can distinctly see, hey, this is my signal, this is my noise. the area of this impulse will give me the signal power, that is the power in the sinusoid. To find the quantization noise power, one thing I can do is I can find the total power in the signal. That you can do by integrating the power spectral density, and then subtract the signal power from it, and that will give the quantization noise, right? So this is signal power. I'll say PQ will be the total power, and that will give you the quantization noise power, and then happily ever after it's done, right?